Welcome to this explainer. If you've ever looked at artificial intelligence and thought, man, this is just a giant mysterious black box, well, you are absolutely not alone. Today, we're popping the hood on these algorithms. We're going to uncover the essential diagnostic toolkit for AI and machine learning by diving into the mathematics that actually make them tick, covering everything from calculus to linear algebra, probability, and statistics.
Now, you might be wondering, why even bother learning the math when we have these amazing, powerful libraries that do all the heavy lifting for us? And look, let's be honest, it is incredibly validating to just type import TensorFlow or PyTorch, load up some data, hit run, and suddenly feel like a master ML engineer. But what happens when the model breaks? What do you do when the accuracy is stubbornly low, or a process that should take minutes is taking days?
Relying purely on coding libraries is really just skimming the surface. Sure, they're fast, they're automated, and super easy to start with. But without the math, it's kind of like driving a high-performance sports car with zero clue how the engine actually works. The math gives you the deep control you need to diagnose exactly why a model is crawling at a snail's pace, or why it's spitting out entirely wrong results. It gives you the power to actually fix the problems, rather than just crossing your fingers and hoping a different library will magically work.
So, to get you that deep control, we're going to follow this diagnostic roadmap. We'll hit calculus, linear algebra, probability, statistics, discrete math, and finally, we'll bring it all together in code.
All right, let's jump right into our first stop, calculus, or basically, learning from mistakes. Calculus is literally the AI's brain. It's what allows the system to learn from its initial errors. Keep in mind, every single model starts out just guessing, and frankly, getting the answers completely wrong. It all starts with a simple derivative, which just measures how fast an output changes when you slightly tweak one single input parameter. Then we scale that up to partial derivatives, doing the exact same thing, but for a bunch of inputs all at once. Next up is the chain rule, which explains how those tiny adjustments pass through multiple layers of a neural network. And finally, we reach the gradient. Think of the gradient like a compass. It points the model in the exact direction it needs to move to reduce its error. So, the big takeaway here is that calculus just tells the model exactly how wrong it is and precisely which direction it should go to improve. Whether you're dealing with simple derivatives or super complex extensions like Jacobians and Hessians, the core philosophy doesn't change. It's all about learning by slowly, iteratively adjusting based on continuous feedback.
Moving right along to part 2, linear algebra, structuring our data.
If calculus is the brain learning from mistakes, linear algebra is the structural skeleton of the whole operation. It's the fundamental language of data. Real-world data is messy, right? Linear algebra gives us the tools to format that chaos into organized tables, lists, and grids, what we formally call matrices. We scale this data up depending on what our model needs to understand. If you just need a single value, like today's temperature, you use a scalar. Need a related list of values, like all the unique features of a single photograph, you use a vector. And when you graduate to really complex, stacked data, like processing thousands of images or frames in a video, you use a tensor. Now, you might hear terms like singular value decomposition, or SVD, and think, no way, that sounds terrifying. But honestly, fundamentally, SVD simply means taking your messy data set and breaking it apart to separate the critical information from the useless noise. It cleans up your data so your model doesn't get distracted and confused by random details.
It's the exact same deal with concepts like eigenvalues and diagonalization. Think of these as mathematical spotlights. They help find the most important directions in your data, where the real, concentrated information lives and where the variation actually matters. These tools make sure our models focus all their effort on meaningful patterns, instead of wasting expensive computing power wandering down useless paths.
Okay, stop number 3, probability, dealing with uncertainty. Since real-world data is incredibly unpredictable and never, ever perfect, probability acts as the AI's intuition. It equips models to handle uncertainty safely. A huge foundational concept here is Bayes' theorem. This is a big one because it fundamentally allows the AI to change its mind. Instead of rigidly sticking to an old, outdated assumption, Bayes' theorem gives the model a mathematical framework to update its beliefs the moment new data arrives. It lets the AI learn from new evidence, dynamically adapting and continuously getting smarter over time.
To manage all this uncertainty, we use specific tools, random variables and probability density functions, alongside various distributions like normal, Poisson, Bernoulli, and binomial. By understanding these distributions, models learn to calculate exactly how likely an event is, rather than just forcing a rigid, unhelpful yes or no guess.
Which brings us to part 4, statistics, understanding the patterns.
Statistics is the dedicated science of collecting, analyzing, interpreting, and presenting data so we can actually make reliable inferences. It is the ultimate reality check for your algorithms. The easiest way to break this down is into 2 buckets. First, use descriptive stats, things like mean, median, and variance, just to see what your data set looks like and understand its basic shape. Then you step up to inferential stats, using tools like hypothesis testing to decisively verify if the patterns you think your model found are actually real or if they're just random, meaningless noise.
To put it bluntly, without statistics, your model is flying totally blind. Bad statistics will literally corrupt your entire machine learning algorithm, causing it to confidently learn the wrong lessons from bad data and generate deeply misleading, completely useless results.
Part 5, discrete mathematics, clear rules and logic.
Now, unlike calculus, which deals with smooth, continuous changes, discrete math is all about distinct, separate steps, clear rules, and strict logic. Think of it like calculating physical paths. If you have a robot trying to navigate a warehouse to reach a specific spot, it can't just smoothly slide through a wall, right? It has to make distinct choices about which clear path to take. Discrete mathematics provides the logical foundation that ensures your AI system can methodically evaluate these distinct choices and pick the absolute best option available.
And finally, part 6, bringing it together in code. Because, let's be real, all these math ideas are just theories on a whiteboard until we actually implement them. They only become powerful tools when we translate them into code, primarily using Python, the most popular AI language in the world. In Python, everything we just learned maps directly to a practical tool. We use basic syntax and object-oriented programming to structure our math into manageable pieces. We import libraries like NumPy to handle all that heavy linear algebra we talked about. And we use matplotlib to visualize those statistical data patterns. We're finally taking all that underlying diagnostic math and turning it into actionable, coded tools. Here's the most comforting, empowering takeaway from exploring this entire roadmap. You do not need to master every single equation at once. You don't need to fear the math, and you definitely don't need to memorize a bunch of scary formulas. You really only need to understand the core ideas of what the math is doing. Once you grasp that calculus finds the errors, linear algebra structures the data, and probability handles the uncertainty, AI stops being a mysterious black box. It starts feeling like a tool you truly control.
So, we've officially lifted the hood. You've seen how the engine actually works and how it runs on a foundation of fundamental math. This diagnostic toolkit is yours to use now. The black box is wide open. The tools are in your hands. So, what are you going to build with them?